Example 5D. 2x minus 3y equals negative 2. Negative 4x plus 6y is equal to 7. Okay? All right. Let's put down our augmented matrix, the first one. Okay? So let's see. There is a, for the first equation, there's a 2 in front of x, a negative 3 in front of y, and then on the other side of the equal sign, you have a negative 2. For the second equation, you have a negative 4 in front of x, a 6 in front of y, 7 on the other side of the equal sign. All right, so here we go. We have got to start with our first column, and we want to put a 1 on the main diagonal. Okay, so I want to change that 2 into a 1. Okay. This one's kind of tough. Switching 2 rows, that's not going to help. That would put a negative 4 in that position. If I multiply or divide by a non-zero number, that would work. I could do 2 divided by 2 and get a 1 there. That would unfortunately introduce fractions. But that may be what we do here, okay? That way, you know, in case you run into a fraction, this will give you some exposure to fractions and working with them, okay? So let's go that route. Let's do row 1. Let's divide everything by 2 because 2 divided by 2 is 1. So that's what we need to divide by there. So let's take row 1, divide by 2. That will become our new row 1, okay? So for our second matrix, row 2 is going to stay the same. Okay, so negative 4, 6, 7, okay? And then we need to take everything in row 1 and divide it by 2. 2 divided by 2 is going to give you positive 1. Negative 3 divided by 2 is going to be negative 3 halves, okay? And then negative 2 divided by 2 is going to be negative 1, okay? So this is our second matrix. Unfortunately, we have a fraction, okay? Sometimes that happens, and you just have to be able to operate with fractions, okay? So this will give us some good practice with that. All right, so we are still in the first column, okay? We have our 1 on the principal diagonal. We need to zero out the rest of the column, so I need to change the negative 4 to a 0, okay? So again, this is where your third row operation is going to come in, okay? I'm going to want to make a change to row 2, okay? So that means I've got to take row 2 and add to it a multiple of row 1, okay? So I have a negative 4 here. A positive 4 would cancel that out, so I'm going to multiply row 1 by 4, okay? So 1 times 4 is going to put a positive 4 right here, and then when I add it back to negative 4, that will give me the 0. So this is going to be my row operation. 4 times row 1 plus row 2 becomes row 2, okay? I'll go ahead and do the work right here. I'll put the matrix over here. So my third matrix, remember we are changing only the second row. So the first row is not changing. So I'm gonna go ahead and write that in so I don't forget, okay? And then let's go over here and do the work, okay? We are going to do, like I said, I recommend you writing out your work. You're less likely to make a mistake, okay? 4 times row 1, okay? So 4 times 1 is 4, okay? 4 times negative 3 halves, okay? You can do this on your calculator, okay? So I know some people aren't great with fractions. You can do, let's see, what was it? 4 times negative 3 halves, okay? So 4 times negative 3 halves, okay? So there you go, okay? It's negative 6, okay? So that's all good. Okay, that was easy enough. Fraction's already gone. Okay. And then 4 times negative 1 is going to give you negative 4. Okay, so that's 4 times row 1. We need to add row 2 to it. So row 2 is negative 4, 6, and 7. Okay, add. So 4 plus negative 4 is going to give us the 0 we wanted. Negative 6 plus 6 is 0. Negative 4 plus 7 is positive 3. That is going to be your new second row, so 0, 0, 3. So I'm going to go put that in the matrix. Okay, We are done with the first column. We've got the 1 on the principal diagonal. We have zeroed out the rest of the column. So we are supposed to move on to the second column now and secure the 1 on the principal diagonal. Okay, so here we are again, just like in example 5C. We've moved on to the second column and we're trying to put the 1 on the principal diagonal, and there is a 0 there. Okay, we talked about this in example 5C. There is no way in the world to change this into a 1. Okay, not possible to change that 0 into a 1. So you have to stop because you're not going to be able to get your goal of the identity matrix, okay, on the left side of the vertical line. Okay, so what we can do here, we're going to try to interpret the solution. We're going to change this matrix back into a system of equations. Okay, so let's do that. All right, so again, when you're doing this, okay, these numbers are the numbers in front of x, these are the numbers in front of y, okay, and then you've got your equal sign. Okay, so if we translate this, what are we going to learn? We're going to learn that in the first row, 1 times x plus -3/2 times y is equal to -1. Okay, I'll go ahead and clean that up. That tells me x minus 3/2 y is equal to -1. Okay, the second equation is going to tell me 0 times x plus 0 times y is equal to 3. Okay, if I clean that up, 0 times x is 0, plus 0 times y is 0. 0 plus 0 is 0. I get 0 equals 3. Okay, and again, how do you make sense of this? Okay, every single time you solve a system of linear equations, no matter how big or small, you have 3 options. Okay, 1, there's either exactly 1 solution, 1 x-y pair that works. Okay, if that were the case here, we would have been able to get to the identity matrix. Okay, so this system of equations does not have a single x-y pair that works. Okay, second of all, there could be infinitely many solutions. Okay, thirdly, there could be no solution. Okay, well, in example 5C, we saw the case of infinitely many solutions. When we translated the matrix back into equations, we got 0 equals 0. That made sense. That's a true statement. Okay, so that indicated infinitely many solutions. Okay, but now when we translated our last matrix back into equation form, we got 0 equals 3. Okay, look at this last line. It says 0 equals 3. Okay, that doesn't make any sense. 0 is never equal to 3. Okay, so we got something that is false. Okay, this is the case of no solution. Okay, so there is no solution whatsoever to this system. Okay, if you were to go back and graph these lines out, okay, they would be parallel lines. They would have the same slope. They would never intersect, so there would be no solution. Okay, all right, so hopefully from examples 5C and 5D, you can tell, okay, the difference between infinitely many solutions and no solution. If you end up with a row consisting entirely of zeros, that is going to be infinitely many solutions. If you end up with a row that has zeros to the left of the vertical line and then a non-zero number on the right side, that's going to tell you there's no solution. Okay, so you need to know the difference.